Hi class, so today we're going to be covering chapter 9.3, solubility. So solubility, this is a picture of a person with gout. Gout happens when your body cannot flush uric acid out of it, and it starts to build up crystals and it deposits in your joints. It's really painful. I know people who have this, and it's extremely painful, and different body parts their limbs swell up because of this. This has to do with solubility. So let's cover what solubility means. Solubility is the max amount of solute that dissolves in a specific amount of a solvent. So let me clear up what this definition means. Say you have a cup of water and you add salt to it, a certain amount, so not just randomly, a certain amount. And it dissolves. You stir it, it dissolves. You add more, it dissolves. You add more, it dissolves. And you keep going until eventually you're going to add some more and it's not going to dissolve. That salt will sit at the bottom of that glass of water. And that means you've exceeded the amount of solute, because salt being the solute, that it can dissolve. And also the solutions all have a max amount of solubility. And once you pass that value, it's going to stay in its solid form. So if I wanted to, let's say that I was close to the solubility value for sodium chloride in water. If I wanted to try to increase it, for most solutions, not all, increasing the temperature actually increases the solubility of the solids going in. However, sodium chloride is not one of them. But if I wanted to, I've been told I don't drink a lot of tea, but if you have tea that's hot and you add sugar, you can have more sugar dissolve than if it's cold. Yeah, I'm new to drinking tea, so that's what I've been told. And this is expressed as grams of solute in 100 grams of solvent, usually water. So when we talk about it, it's usually water, and it's based on 100 grams, which means you have 100 grams of water, and how many grams of solute can handle being soluble in 100 grams of water. Okay, so there's two terms, and they might be a little confusing at first. Unsaturated. Unsaturated is what we normally deal with. We have water and we add salt, it dissolves. That means it's unsaturated. It can keep dissolving. It is less than the maximum amount of solute, and you can keep adding more and more because you have not reached that solubility value for the salt in water. Now, saturated is opposite. Not opposite. It means that it is done. You have exceeded the solubility value, and now everything's going to sit at the bottom. Well, what you don't understand when it's a saturated solution is that you just see salt sitting at the bottom, but there's actually an equilibrium going on. And what happens, see these reverse arrows again? You have a solute and a solvent. And what happens is when you add the solute dissolves in water. Unless you hit the saturated solution. The saturated solution is what's sitting here, all these salt crystals at the bottom. This is equilibrium constant. So what it means is that for every solute that dissolves, a solute recrystallizes, and this is at the same rate. So when one goes in, the other one goes out, same rate constantly. That's what an equilibrium constant means. So the more salt you add, one's going to dissolve, another's going to recrystallize. And it's constantly happening, even though we don't see that happening here. We just see a bunch of salt sitting at the bottom. So a saturated solution, more solute can dissolve, obviously, in an unsaturated solution, but not in a saturated, because of the fact that it's already hit the max capacity of what it can dissolve. And then the rest will just sit there. This is called a brine solution. I actually make these at my work in my lab, because we need brine solutions to clear out impurities for reactions. Well, I used to. And I purposely would do this. I would saturate water. I would add salt throughout the day until I had a couple inches thick of salt. I need that actual saturated solution to help me with my reactions. Or I used to do this. So if you add salt and you see it dissolve, it's very few crystals. It's unsaturated, meaning you can keep adding. Like if you're trying to boil water, you can add and add. But if you are at max capacity, one will dissolve for every one that's recrystallizing. You won't see it. You'll just see this solid sitting at the bottom. Identify each of the following solutions as saturated and unsaturated. Salt disappears when you put it in water, so it's dissolving. That's pretty easy. That's unsaturated. Sugar added to a cup of water that does not disappear but sits at the bottom. You've hit max capacity for solubility, and it is saturated. So there it is. When it can still dissolve, it's unsaturated. When it cannot dissolve, it is saturated. Okay, so now we're starting to look at values of solubility. So here at 40%, at 40 degrees Celsius, the solubility of potassium bromide is 80 grams per 100 water. So that means that 80 grams of potassium bromide will dissolve in 100 grams of water. If you do 81.1, 80.1, 85, you're going to start seeing those solid crystals sit at the bottom. This is the max that it can be dissolved. Identify the following solutions as either saturated or unsaturated and explain. So let's take a look at this first one. We have 60 grams of potassium bromide added to 100. So we're dealing with the same ionic compound, just different values. So 60 to 100 is less than 80. So this one is going to be unsaturated. It's way less than the max value of solubility. It's still going to dissolve in. Now we have 200 grams potassium bromide added to 200 grams of water. This one is going to be saturated, and all you have to do is look at the ratio. This is 80 to 100. This is 200 to 200. So this would have to be 100 to 100, and it's not. 80 is not reaching 100. So this is going to be saturated because it's past the 80 per 100 ratio. And the last one, 25 grams added to 50 grams. So this one is now cutting down the water, and we're looking at a different value that doesn't exactly match up with the 80. But if we pass it, if we look at it, half of 80 is 40. So 25 is less than the 40. So it is still less than the solubility of the 80 per 100. Now, effect on solubility. Solubility depends on temperature, and most solids increase solubility as the temperature increases. However, gases do the opposite. Gases will decrease as temperature increases, and we'll talk about that in the next few slides. But I want to point out some things here. So we see potassium iodide. As we start increasing the temperature, then the solubility actually can exceed the value at room temperature. But if you cool it down, that will actually recrystallize out. And that's a purification method that we use called recrystallization. So we do this on purpose. So here we increase the heat, and we can add more and more solute, and it will dissolve as the temperature goes up. And you can see all of these are going up except for sodium chloride. It is flat at 40. That means that even with temperatures increasing, you will only dissolve max amount of approximately 40 grams per 100 grams regardless of temperature. Has no effect on it. Okay, so let's take a look at gases. Gases are the opposite. These are going down. So you can see if they start at 0 and the solubility starts going down, down, down as it goes up. So solubility for oxygen is about 7.5, let's say approximately. And as the time you get to 40, it's below the solubility is less than 4 milligrams per 100 grams. And it's the same for all of these. Why is gases different than solids? So the solubility of gases decreases as the temperature of the solution increases. That has a lot to do with energy. Energy gives these molecules more freedom to leave from the solution. So if you're boiling something, remember heat is energy, and it's touching these compounds, these molecules. If it has enough energy now, it can leave the solution it's in. So why could a bottle of carbonated drink possibly burst or explode when it is left hot out in the sun? Why do fish die in water that is too warm? That's one of the reasons why there's a big concern with the ocean even going up a degree, because a degree may seem like it's a small amount, but for an ocean, that's a huge deal. And something that, some fish may be so sensitive, this could kill them off. The pressure in a bottle increases, so it's a closed, if you ever left soda in your car, increases as the gas leaves. So as it gets hotter and hotter, let's say the soda is starting to heat up. It's giving those molecules in solution energy to leave, the CO2. So the CO2 is leaving at a faster rate. However, they're stuck in a sealed bottle, so, or can, they can't go anywhere. So eventually enough of that CO2 is going to leave the soda, and let's say it's over 100, and explode because there's so much it just bursts. So the pressure in the bottle increases as the gas leaves solution when it becomes less soluble at higher temperatures. As their pressure increases, the bottle could burst. And for the ocean, because oxygen is less soluble in warm water, fish cannot obtain the amount of oxygen required for their survival. Remember, O2 is in the water, and it will leave the surface if it can, if the water's warm. It's giving it enough energy to leave. So now we're going to cover Henry's law. This is solubility and pressure. Henry's law states that the solubility of a gas in a liquid is directly related to the pressure that gas above the liquid. At higher pressures, more gas molecules dissolve in liquid. So this has to do with pressure. So when they put CO2 in soda, I've been told, and I've read it somewhere, it's under extreme high pressure. Why is that? Because the pressure that can push down all those CO2 molecules into the can of soda, and then they seal it. So the molecules have nowhere to go. They are stuck under high pressure and they will stay in liquid. However, if the pressure is relieved, like when you open it, you hear all the fizzing, you hear all the CO2 removing itself from the solution, because the pressure that was keeping it down, think of like a big hand, it's not there anymore and it can leave. Same as atmospheric pressure. The higher we go, the pressure is not as strong, so more molecules can leave, if you're trying to boil something, because the force isn't there to keep those molecules in the water. And this just tells you here what's happening in a sealed can of soda, and the gas molecules will, if it's higher pressure, you'll have more molecules that go into the liquid. If it's lower pressure, you have less molecules that are soluble in there because they can actually leave very easily. That's why you want a cold soda has better solubility of keeping the CO2 in the solution than a warm soda. The warm soda, the CO2s have enough energy to leave the soda and it'll be flatter quicker. So now we're going to discuss soluble and insoluble ionic compounds. So we're going to use the double displacement reaction or double replacement reaction to determine if a solid precipitate can form. Now here is this is a chart of solubility rules. Now they're way more expansive than this, but for right now, this is what we're going to look at. Only ionic compounds that contain a soluble cation or anion are soluble in water. In an insoluble, which means it forms a solid ionic compound, the ionic bonds are too strong for the polar water molecules to break. We're going to use these rules to determine if a reaction will result in a solid. And we're going to break it down using ionic compounds, ionic equations, and net ionic equations, which you guys should all know how to do. All right, we'll cover that in a few slides. This is pictures of very colorful insoluble ionic compounds. This is what happens when you don't have what you're working with isn't listed here, or does not have a cation or anion attached to it. And I'll explain what this is in a minute, but let's go back to this. So if an ionic compound contains a combination of a cation and anion that are not soluble, then the whole compound's not soluble of what you are producing from the double replacement reaction. So in this case, this is a product of cadmium and sulfide. This is iron and sulfur, and this is lead and iodine, or iodine. I'm not talking about the whole reaction here. And nickel hydroxide. Forget what I'm saying. I'm mumbling here. Anyways, these are all not soluble, and you can see that solids are starting to form. So let me go back and read this to you. How do you use this? Well, you have positive ions. So if you have something that has any of these ions attached to it, so you have anions that are attached to these, they're going to be soluble because these are the partners that get them in the door. Think of it like a secret club. Negative anions, any of these, this is acetate, nitrate, same thing. If they're attached, they're going to be soluble in water. Now we have sulfates. Sulfates are soluble except when they're paired as barium sulfate, lead 2 sulfate, calcium sulfate, strontium sulfate, or mercury sulfate. Anything else, like any of these cations that are attached here, they are soluble in water. It's these 1, 2, 3, 4, 5. If any of these 5 are attached to the sulfate, it is going to create a solid. Now here we are at the chlorides. If you look at the chlorides here, we have chloride, bromide, and iodide. Now they are all soluble except for when they're partnered with any of these, silver, lead, or mercury. So if this is with sodium chloride, it's soluble, but if it's paired with lead to chloride, now it is insoluble. So these are things that you should be able to be comfortable reading because they can be quite confusing, so you should get used to looking at this. Okay, so here is sulfates are soluble, which we already covered, unless it's with one of these 5. Barium sulfate is an insoluble ionic compound used to enhance X-rays, and we definitely want this to stay insoluble because barium is extremely toxic. It would kill the patient if they took this and it was soluble. So this is on purpose. They're using an insoluble ionic compound, and it's meant to stay insoluble the whole time it's in the person's system. But as a solid, it's serving a purpose to help looking at this person's health. Okay, so insoluble rules, here are some more we can look at. Potassium sulfide is soluble in water. Reason, because it's attached to potassium. All nitrates, anything attached to a nitrate is soluble. So I don't even need to look at what this is. I just know nitrate has that free pass into that secret club no matter what. Chlorides has some exceptions, and lead is one of them. So this is going to be a solid. And sodium hydroxide is soluble because it contains sodium. However, some hydroxides are not. And then we have aluminum phosphate, and it is insoluble, contains no soluble ions. So this one didn't have any, it's going to be a solid. Okay, so let's break down whether these are soluble or insoluble. So we had cadmium sulfide. That one is, we covered it here. It's the first picture, and that tells us it's insoluble. Compounds are generally insoluble. Cadmium, yes, definitely, and that's dangerous too. And sulfide. Now we have sodium sulfate. Sodium is on our chart as a solubility, that it would be soluble in water. So we anticipate that this is soluble. We also have sulfur. We don't always have both cation and anion listed. So you have to always go by the one that you do see and not worry about the one that you don't. In this case, because the exceptions will always show. In this case, we have both. So it's a sulfate, and it's not with one of these, so it's soluble. It's sodium. Doesn't matter what the other part is. It's soluble. We have lead to iodide. We have iodide soluble, except when we have lead. So we do not expect this to be soluble. It will create a solid. And we have nickel nitrate. Nickel nitrate. Nitrate is here, and all nitrates are soluble. So we don't even need to worry about what this other one is, and it is soluble. Okay, so now we get to a problem where we're going to have to break this down. This can take a little time. Take your time. Make sure you understand double replacement reactions first, because that's what this is. You should be able to put this together and break this down completely with physical states. Physical states tell you everything you need to know when we're dealing with these, because we're looking at physical states to determine which one is the solid. All right, we will use solubility rules to predict whether a solid, called a precipitate, forms when two solutions of ionic compounds are mixed. What precipitate forms when solutions of lead to nitrate and potassium sulfate are mixed? So we're going to mix these up, and now we have a double replacement reaction. So we're going to have to switch partners. So we're going to have to switch partners on these, and we do the crisscross method. Not balanced. Nothing will be balanced till the end, or as we get close to the end. Well, let me take that back. Nothing's going to be balanced right now in step 1. And the main goal here is putting them together and keep the charges the way the charges need to be. Okay, so if you have to separate it out so you can see the partners, this is one way to do it. I don't do it this way, but if you're learning, it is better to try to put them in a way that helps you. So if we look at lead and sulfate, this is an insoluble product. Yet potassium nitrate, I told you all nitrates are soluble, is soluble. So now we know the product from the double replacement, that's going to be a solid. So you would normally write a molecular equation having both of these with the arrow and then the products, which would be potassium nitrate and lead 2 sulfate. That would be a molecular equation. Here, they're not asking for that. They're asking for the ionic equation, and that means the total, everything broken up into ions, so we can see which one is the solid. So here is lead 2. This is why breaking it up like this might be easier, because then you just write everything out into a regular reaction. So we write everything out with physical states. This is aqueous, 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 aqueous. However, we have to show the solid, and then we have aqueous and aqueous. If you notice, we have a 2 potassium ion cations here, and we have 2 potassium cations here. On the other side of the arrow, the reactants. And we have 2 nitrate ions here on the reactant side, and we have 2 nitrate ions on the product side. So these are called spectator ions because you see they look alike. Nothing's changed for them in the reaction. So they're just spectator. They're watching the ball game sitting in the seats. What is not part of that does affect the reaction, is whatever creates the solid. These are important ones. These are what affect and produce the precipitate. So we go from, you write the net ionic equation. You may be asked to remove the spectator ions or circle them or put a line, and you would do that, showing the net ionic, the ionic equation. We would cross out if we wanted to know what the net ionic equation is. The net ionic equation is only the ions that produces the solid. So this part here is the ionic equation with things being crossed out so you can see how we got to the net. And the net only involves what produced the solid, and that's it. The rest of it is removed out of it if you're asked for a net ionic equation. That's why I put them in bold so you can see which ones are which. And that is it.